Section 4.3 is about complements and conditional probability. Let's start with complements. First, the probability of at least one means one or more. So if you have, for example, five events, elements of event 1, 2, 3, 4, 5, and we want to see if there's if at least two of them are happening. So that means we start here. Two of them, that means either 2, 3, 4, or 5. If we say at least one of them, that means 1, 2, 3, 4, or 5. At least four of them means 4 or 5. So the word at least is important when we read problems about probability. The complement of at least one. Now if we focus on at least one, that means, for our example here, if we have elements 1 or outcomes 2, 3, 4, and 5, at least one means one or more. 1, 2, 3, 4, 5. So what is the complement of that? The complement of at least one is none of them. So the complement of getting at least one means we get non-occurrence of the event. Okay. So we denote by A, for example, capital letter A, or B, or C, or one of these English alphabet capital letters, event. Here in this section we'll focus on at least one, that's the event A, and the A complement. As you can see, A bar is read A complement, or complement of the set or the event A, getting none of the event being considered. And from the last section we know that probability of an event plus probability of its complement is equal to 1. For example, if the event consists of those three elements, this is event A, the complement of this is the element 1, so the sum of the probability is the probability of the whole sample space, which is equal to 1. So when we say probability of A plus probability of A complement, that's equal to probability of the sample space, which is equal to 1. Now if we know probability of A complement, then we can find probability of A by applying same formula as of this. So probability of A is 1 minus probability of A complement. Let's take some examples. Here we want to describe the complements. When 4 digits, I mean 0 to 9 inclusive, are randomly selected with replacement for a lottery ticket, at least one of the digits is 0. So the event A can be defined as at least one of the digits is 0. Now what is the complement of that? None of the digits is 0. Now let's take another example. If you make random guesses for 10 multiple choice problems, you have 10 multiple choice problems. And each one of them consists of 5 choices, or 5 possible answers. So A, B, C, D, E, and that's for all questions. Now the question is, what is the probability? Now here's the question. What is the probability of getting at least one correct answer, or of getting one question with correct answer? Okay. So we first define the event A. We usually find the event A after the word probability, the question of probability, we see here, what is the probability of what? Of getting at least one correct answer. That's the event. So getting one correct answer. Let me write it as getting one correct answer. Now, what is the complement of that? Complement of that, all of them are wrong answers. None of them is correct. Now, after defining this, we have 10 questions. Now, if we just pay attention to one question of them, we find that to get a correct answer, the correct answer is just one of these answers, A, B, C, D, E, one of these options. So, or one of these possible answers. So, what is the probability of getting one correct answer? It's just 1 out of 5 answers. So that's probability of A, just for one question. But for the 10 questions, we need to do this for each question. So probability of A here, probability here of getting correct answer is 1/5, here 1/5, and so on. We can find the probability by applying the complement. Probability of A of getting one correct answer is 1 minus probability of getting none of them is correct. Now, how to find probability that none of them is correct? We can find probability of the complement. Now, if the probability of getting one correct answer, the first question correct, is 1/5, what is the complement of this? 4/5, because we have, if the correct answer is B, then the rest of them are not correct. How many ones? We have 4 other answers out of 5 answers. So that's the probability of choosing one incorrect answer. And that's the same thing for the second question. For the third question, we have 4 wrong answers and 1 correct answer. So probability of getting incorrect answer is 4 out of 5. And here, same thing, up to the 50th question. Now, how to find this probability? So here, 1 minus, what is the probability of A complement? That means the first one is not correct. The probability here is 4/5. And means multiplication. The second one is not correct. And the third one is not correct. Up to the 10th one is not correct. So this is the probability of getting one correct answer. 1 minus none of them is correct. Getting at least one answer, that means 1 or 2 or 3, 4, 5, or all until the 10th, all of them are correct, all questions. Okay, now we find this 1 minus, as you can see, we have 10 answers, 10 questions here. So we write 4/5 raised to the power 10. We just multiply this by itself 10 times, so we can write it this way. Now we use the calculator to find the probability, which is 0.893. So there is 89.3% of chance to pass the course just by guessing the exam. So we have 89.3% chance to pass the exam only by guessing the answer, the correct answer. Okay. Now, question or example 3. Here we have a company supplies a CD of Bruno Mars, 24K, and lots of 50. So this is number of elements in the sample space, or the sample. It's 50 disks, and they have a reported defected rate of 0.5%. So the probability of an individual disk being defective is 0.005, because it's 5%. Okay, now we have, it follows that the probability of a disk being good is 0.993. 0.95, because this is probability of A. If we want to define A first, A, at least one defective disk is existed in a lot of 50 disks, and the complement is none is defective. So that means all the 50 disks are not defective or good. Now, what is probability of A? Probability of A is given, it's 0.005. And what is probability of A complement? Probability of A complement is 1 minus probability of A. But what is probability of A? It's 0.005, and that gives us 0.995. Okay, now we want to find probability of A. So probability of A is, because the question here is what is the probability that the control engineer Choi getting at least one defective disk in a lot of 50 disks. So we are asked to find the probability, that's the question, and here's the probability of getting at least one defective, that's the event A. So we want to find probability of A, which is 1 minus probability of A complement, and that's 1 minus 0.995. Now, but this is applied for how many disks? We have 50, so we need to raise this to power 50. Because this is correct now, this is the for just one disk that's not defective. But for the whole 50 disks, we need to multiply this by itself 50 times. And that means we can write it this way. We can write 0.995 raised to the power 50. And then using the calculator, we get 0.222. Now, problem 4, we have a statistics student plans to use TI-84 plus calculator on her final exam. From past experience, she estimates that there is 0.91 probability that the calculator will work, and that means 0.09 probability that it will not work on any given day. Because the final exam is so important, she plans to use redundancy by bringing in 2 TI-84 plus calculators. She wants to bring 2 calculators just in case. Now the question is, what is the probability that she's able to use to complete her exam with a working calculator? Now here, she can do that. She can complete the exam with one working calculator if at least one of them works. So that means we can define the event A here. The event A is that at least one calculator work. Now, what is the complement? None of the 2 calculators will work. Okay, so we define the event and its complement, and then we find the probability of A, that at least one of them will work. Now, probability of A is 1 minus probability of A complement. But what is probability of A complement? Probability of A complement for just one calculator is 1 minus 0.091, because 0.091 to this is the probability that one calculator will work. So will not work, that means 0.005. 0.09. For two calculators, so probability of A complement is 0.09 for the first times 0.09 for the second. So the first one will not work and the second one will not work, so we get 0.09 raised to power 2. Now we can find the probability that at least one calculator will work. That is 1 minus this number here, 0.09 raised to the power 2, and after computing this we get 0.992. Now, does she really gain much by bringing in the backup calculator? The answer is yes, because in this case she reduced the possibility of getting the exam not be work because of the calculator. So with one calculator exam without a working calculator, with one calculator the probability of getting not working calculator, or the exam will not run if it depends so much on the calculator, is 0.09. What about two calculators? For two calculators it's 0.008. Because from here, for two calculators, this is two calculators, we have 1 minus 0.992, which is 0.008. For two calculators, the exam's working with this, not working with this probability. For probability 0.008, the exam will not work. That means two of them will not, the calculators will not work. So this should be 81, but because 9 times 9 is 0.09 times 0.09 is 0.0081. So as we can see, probability gets better for the calculators to work, for at least one of them to work. Okay, so now the second part is about conditional probability. For conditional probability, we have a condition here applied. So when we have some probability of an event, given that event A has already occurred, we write this as probability of B given A, probability of the event B given A. That means probability of the event B given that the event A has already occurred. Now, what is the rule that we use? This is the rule that we use. Probability of B given A is probability of B and A, and as you can see, I use this notation to mean and. So B and A over probability of the condition event, which is probability of A. So we need to remember this, and the keyword is the given. This is the keyword. Now, if A and B are independent, then probability of B given A is just probability of B, because A will not affect the occurrence of the probability of the event B. And in general, probability of B given A is not equal to probability of A given B, as we'll see in next examples. Now let's take an example here. Here we use the following data from the previous section, and here we have people or subject uses drugs, subject does not use drugs, and here positive test result after testing those people. And this sample of 555 people, we find that, for example, 45 have positive results while they actually use drugs. 25 have positive test results while they are not using drugs, and here negative test, 5 people are not using drugs where the test is negative while they actually use drugs, and for 80 the result is negative, while they are actually don't use drugs. Now, after paying attention to these numbers, we want first to find the probability that, or before that, if one of the 555, here the sum of all these numbers, or the sample size, is 555. So we select one of them at random, and we want to find the probability. Now we start defining the event. Probability that the subject had a positive test, let's call this event A, given that's conditional probability that the subject actually uses drugs, this is event B. So we want to find probability of A given B. Now, applying this formula here, this is probability of A and B over probability of B. Usually have this here, probability of the condition event. Now, probability of A and B, what does that mean? That means the subject had positive result and actually uses drugs. So that's 45, but 45 out of 555. This is probability of A and B over. Now we want to find probability of B. Probability of B is probability that the subject actually uses drugs. How many subjects use drugs? Here, as you can see here, we have 45 plus 5. So that is, the sum here is 50. So we have 50 over the total number of subjects is 555. We can cancel this number with itself because it's denominator of both fractions. So we get 45 over 50. Now, finding this using the calculator, we get 0.9. That's the probability that the subject had positive result given that the subject actually uses drugs. Now, part B, if one subject is selected from those 555 subjects, we want to find the probability that, now we start reading the events, that the subject actually uses drugs, but we call this B in the previous example, given that this means conditional probability that he or she had a positive result, test result. This is A, event A. Now we want to find this probability of B given A. That's applying the formula B and A over probability of A. Now, after writing this, what is probability of B given A? B intersect A, or B and A, it's the same as the numerator here. It's 45 over 555 divided by probability of A. What is A? A is the probability of the subject actually uses drugs. Or no, probability of A. A is the subject has subjects have positive test result. They have positive test results here. This is positive test results. How many subjects are there? We have 45 plus 25, that's 70. So we have 70 out of 555. And then we can simplify. We get 45 over 70, or you can just use the calculator from here. And using the calculator, we get 0.643. That's probability of B given A. And as you can see, this is not equal to probability of A given B. Those are not equal, right? So in general, probability of B given A is not equal to probability of A given B. Now another example. Here, a middle school. At a middle school, we have 16% of the students play football. So probability of people or students who play football is 16%. That means 0.16. when we write it as a probability, because probability should be from 0 to 1, so it's 16, 0.16. But this is 16% play both football and basketball, so let me modify this. So football and basketball. Now we have another probability or another percentage of students who only play football. That's 32%, which is 0.32. Now we want to find, here's the question, we want to find the probability, what is the event that a given student plays basketball given that the student plays football. So that's probability of playing basketball given that the student plays football. Or you can use simples A and B here, and you use the formula above. Okay, now this is probability of the intersection of them, basketball and football, that means play both of them, over probability of the conditioned one is, that's the football. Now probability of playing basketball and football is 0.16 over probability of playing football, only football, is 0.32, and after using calculator we get 0.5 or 50%. Now the last part is about Bayes' theorem, and here in this section we'll not focus on the formula for Bayes' theorem. There is actually a formula for Bayes' theorem that's based on the conditional probability, but that's we will avoid it here. We just focus on how to apply Bayes' theorem, even if it's implicitly, or just understand that there's some condition here applied to the result. We'll just discuss one example and see how to apply Bayes' theorem. As I mentioned, I will not use formulas here, but I will show you how to use this theorem implicitly. Now here we assume that people who have cancer in some population is 1%. This is the prevalence rate, and so we use C to denote people who have cancer, so probability of C is 0.01 for subject randomly selected from the population. Okay, now we have some results. Probability of C of selecting one person and that person has a cancer is 0.01. It's given here. Now the false positive rate is 10%. What does that mean? That means the probability of getting positive result given that the cancer is not present. So the probability here is 0.10. And we have another probability here. True positive rate is 80%. That means probability of having positive result given that the cancer is present, this is 0.8 or 0.80. Now the question is, what is the probability of having someone who has cancer given, or getting someone who has cancer given that, this is given that, or conditional, that the result is positive. So we want to find probability of having someone who has cancer given that the result is positive. So here we look at Bayes' theorem this way. We have some people, or sample of people, and then we make some tests for the cancer, and we have some results, positive and negative. Now I ask you about the starting from results. I suppose that the result is already there, and I ask you if that result comes from a person who have, or that the result is for some person who already has cancer. So here people who may have cancer or not having cancer, that's C bar or the complement of the people who have cancer. And then the test can be positive or negative, and here positive or negative. And here in this question, probability of C of having cancer given that the result is positive. So we already know that the result is positive. Now what's the probability that the person has cancer? So this is how Bayes' theorem starts. We start from the end, and then we're asked about the original subject, so whether they have cancer or not. Okay, so we start from right to the left. Now we want to find this probability of selecting some person who has cancer, provided that or given that the result is positive. Okay, now we want to do that. So before we do that, since we have we should find some numbers, because we have here probability of C, here we have probability of or conditional probability, here we have another conditional probability. So it's a good idea to fill the following table. So here we have people who have cancer and people who don't have cancer. Now how many people of that sample have cancer? Now here let me suppose that the sample size is 1000. Let me add this to the question. Now the total here is 1000. Now how many people who have cancer in this sample? We have 1% of them. That means 10 people. 1% of how many? Of 1000. That is 1% times 1000. So we cancel 2 zeros, we get 10. So we have 10 people. But how many of them have positive result and how many of them have negative test result? Now for positive result, we know that positive given that, for example, here we are given some probability. If we read here, the true positive rate is 80%. That means probability of positive result given that cancer present is 80%. 80% of whom? The total number of population or the sample, or just the 10 people who have cancer? It's just for the 10 people who have cancer. So it's 80% of the 10 people. So we cancel these zeros, we get 8 people. So 8 have positive result, test result. Now what's the complement of that? It's 2. 2 have negative results because the sum is 10. The sum is 10. 8 have positive results and 2 have negative results. Now people who don't have cancer. Now we know that since this is the total here is 10 and the sample size is 1000, people who don't have cancer are 990. If you find the sum here, you get this number 1000. Now how many people don't have cancer but have positive result? Now here we use another probability. We have here false positive, 10% for false positive. So positive result but people don't have cancer is 0.10. Just gonna wait for a second to charge the iPhone pencil, so just a second. Okay, let's try it now. Okay, now here false positive, that means here, as you can read, it's false positive. So here it's the false positive is 0.10, and that's 10%. So 10% of how many? Of 990, the people who don't have cancer. So just remove the zeros from, or just multiply them using calculator. We find that there's 99 people or subject or members of that sample who don't have cancer but their test is positive. Now, how to find the number here? Negative test with no cancer. Actually, we have the sum here. The sum is 990, and we already have 99 who have positive with no cancer, positive test with no cancer. So we just subtract 990 or 99 from 990, and that will give us 893. Okay. Now, after finding these numbers, we go to our question. Our question is find the probability of selecting someone who has cancer, given that the result is positive. That's probability of having cancer and the result is positive over probability of the positive result. Now, having cancer with positive result, how many people? We use a different color. Having cancer with positive result, we have 8. So 8, but this is not a probability. This is 8 out of 1,000 people. That's the sample size. So or the sample space size. We usually divide by that when we find the probability. Now, what's the probability of having someone who has positive result? So here, positive results, all those people have positive results. So the sum of those is 107. So we have 107 out of 1,000. And then we cancel 1,000 here, or just use the calculator. You get 8 over 107. Using calculator, it's 0.0748.